Hey, welcome. You ever just stop and think about the microchips inside your phone or your computer? I mean, how do they perform trillions of operations without a single glitch? It seriously feels like magic. But behind all that perfection, there's this invisible guardian, kind of like a mathematical referee, making sure every single signal wins its race on time. So today, we're going to pull back the curtain and see how this guardian actually works.
I mean, really think about it for a second. Inside the very device you're using to watch this, there are literally billions of electrical signals zipping around at almost the speed of light. If just one of those signals is late, even by a nanosecond, your favorite app could crash or your whole system could just fail. So how on earth do engineers manage this ridiculously complex traffic problem?
Well, the answer is this absolutely brilliant process called static timing analysis, or STA for short. And this isn't about running a bunch of tests and just, hoping you find a bug. Nope. This is about mathematically proving the design is correct from the get-go. It's the ultimate referee for that high-speed race happening inside every circuit we use.
So what is it exactly? Well, STA is a method that checks every single possible path a signal can take through a circuit. Imagine trying to check an entire country's train schedule, every single connection, every transfer, to guarantee that no one could ever miss a train. And you do all of that before a single train even leaves the station. That's STA. No simulations needed, just pure exhaustive analysis.
Now you might be thinking, well, how does this stack up against the alternative, dynamic simulation? It's a great question. Simulation is kind of like test driving a car on a few specific roads. It's useful for sure, but it can't possibly cover every single scenario. STA, on the other hand, is like having the car's complete engineering blueprint and mathematically proving it can handle any road anywhere in the world. It's exhaustive, it's way faster for these massive designs, and it is just incredibly reliable.
Okay, so how does this mathematical referee actually enforce order? It all boils down to a fundamental set of rules. You could almost call them the physics of time within a digital circuit. Let's break down the most important ones.
To enforce its rules, STA is constantly juggling a few core concepts. But to really get a handle on how this all works, we're going to zero in on two of the absolute biggest ones that act as universal laws for every signal: setup time and hold time. If you understand these two, you're well on your way to understanding how our devices work so flawlessly.
First up, we've got setup time. The best way to think about this is with that train analogy. Setup time is the rule that says you absolutely must be on the platform, ready to go, before your train's doors close. In a circuit, the data signal has to arrive and be totally stable before the clock signal comes along to capture it. If it's late, whoops, it misses the train, and the system gets corrupted. Totally unpredictable data. Not good.
And then we have the second big rule: hold time. Sticking with our train analogy, this is the rule that says you have to wait on the platform until the train has safely pulled away before you start moving around. In the circuit, the data signal has to stay perfectly still for just a moment after the clock edge has passed to make sure it was captured correctly. If it changes too soon, the data gets all garbled. It's like trying to read a sign on a train that's already blurring past you. The result? Another error.
So, okay, these two rules might sound pretty simple on their own, right? But applying them flawlessly across an entire chip with millions of paths, that is what makes all of our modern technology possible. Understanding why STA is so indispensable really reveals the quiet genius behind modern chip design.
And just to give you a sense of the scale of this challenge, a modern microchip, what we call a very large-scale integration, or VLSI design, it doesn't have hundreds or thousands of these paths. We're talking about designs with well over 1 million logic gates, which create millions, even billions of connections. STA has to mathematically verify every single one of them. It's a task of just staggering complexity.
And this is exactly why STA is the undisputed industry standard. It gives you 4 key advantages that are just impossible to ignore. You get exhaustive coverage of every path, no exceptions. You get the speed to analyze these huge designs quickly. You get the reliability to catch super costly errors before a chip ever gets manufactured. And you get the scalability to keep up as chips get more and more complex. So where does this all fit into the actual chip design process? It's definitely not an afterthought. STA is a critical step. It's like the final gatekeeper that comes into play after the initial logic design and the physical layout are done. It's the final check that verifies the entire design against its timing budget before it gets the green light for fabrication. But the story doesn't end there. Of course it doesn't. As our chips get smaller, faster, and way more powerful, The job of this invisible guardian is actually getting a lot tougher. The challenges are constantly evolving, pushing the absolute boundaries of physics and time.
I mean, engineers today are dealing with some incredible new complexities. Tiny variations in manufacturing mean no two chips are perfectly identical, so a timing path that's safe on one chip might be too slow on another. Your phone heating up in your pocket can literally change the signal timing inside. And get this, many modern chips have multiple clocks running at different speeds. It's like a conductor making sure instruments playing to totally different beats still come together in perfect harmony. STA has to account for all of it.
So when you put it all together, it becomes pretty clear why experts consider this process so fundamental. As one analysis puts it, static timing analysis isn't just another tool. It's a cornerstone of digital design verification. It's what gives us the confidence that these incredibly complex circuits we all rely on every day will actually, work.
So, the next time your phone seamlessly loads an app or your computer crunches through some complex data, maybe give a little nod to the invisible guardian, static timing analysis. It's the silent enforcer of order that makes our entire digital world possible. And that leaves us with one final, fascinating question to chew on. As we continue to shrink our chips down, approaching the atomic scale, what new, mind-bending rules will time demand from us next?